Good morning and welcome to Math 108. So let's get going. So as you remember, previously what we have talked about was our basic or called ordinary differential equations. And we saw that they had similarities between these kinds of equations and our original learned in school number equations. But what we mean by a solution is a function that satisfies a differential equation. And we had equations like maybe x times dx dy minus 1 equals 4x cubed, for example. And then we saw, okay, well, let's isolate our derivative. We're looking for a function that has that satisfies this information. In order to find that function, one option is to isolate the derivative portion, and then we will have let's do it in two steps, 4x cubed plus 1, and so dy dx equals 4x squared plus 1 over x, for example. Then we can say, well, we're looking for a function whose derivative is exactly this right-hand side. That is exactly the same as our antiderivative question. So we can go and say, well, our function, which is a function of x, is therefore the indefinite integral of what we have on the right. Okay, so for the very, very simple kind of equation, we can just recognize our differential equation as the same as a rephrasing of our antiderivative question. And then we can go ahead and say, well, okay, y is, well, I leave the 4 out in front. I have an x cubed with a correction, and this one is going to be natural log of x, and I add my c and so on. So before we worry about a particular solution, let's just get to the general solution, because that's the part where we solve the differential equation. So in the very basic situation, the one where I just have x's in combination with my derivative dy dx, then by isolating dy dx, I can just recognize it as a rephrasing of our familiar antiderivative question. The problem, however, is what if we have more complicated differential equations? Not like this example where we just have x's, but maybe there are some y's in there as well. So what about an equation like, let's say, y dy dx? Sure, there can be some x's here. Maybe there's an x squared, and maybe the other side just a 1. What about an equation like that? Now, recognizing it as a straightforward antiderivative question is not as easy for us. So what we're going to branch out to and expand on what we have is identify a new type of differential equation. And it's going to be a separable equation. That's going to be its name. And what that is going to be is we're going to have, it's going to be any differential equation that you can write in the form dy dx. And of course, the variables could be different, but the idea is the same. Now, it doesn't really matter here. I have a function in y, and I have a function in x, separated by this divider line to have all the y variables on one side of the line and all the x variables on the other side of the line. Now, it doesn't matter which side they occur, as long as I have them like that. Actually, maybe I'll prefer the second one. It doesn't matter at all. I want to be able to separate them, or I can go even further, or I can have, let's focus on this one and recognize that we can write, no, the function doesn't actually matter, right? I can recognize that I can write it like this, have only y's with my derivative and only x's on the other side. Let's maybe focus on something like that. So we're able to separate the variables, the x's and y's that could be floating around. We're able to separate them from each other. This one is, this top example is a separable equation because I can write it like this. Maybe this is the easiest version to get a handle on, the one in the box, though I can do it, I can see the general form in different ways. Perhaps this is the best one. When I have the derivative with all the y's with it, and on the other side of the equation, all the x's, then it's going to be a separable differential equation. So we want to level up our ability to solve differential equations by looking at more complicated differential equations like this. And that's the only type we are going to look at. Now, for these kinds of equations, we have a very convenient method to help us figure out what the solution is. Let me just make a new page. To get an idea of how this method works and to show that it's not that strange really, let's just note how we've solved a basic differential equation. Let's just not have any y's in it. Let's just take a 2x. Nice and simple. What have we done before? Well, the very first thing we did was we recognized what this information is and realized that it is simply asking for my antiderivative question. It is simply asking the antiderivative question, and then I can go ahead and find that antiderivative, and I have a solution to the equation. Okay. Another way we can see this very same simple example is see the derivative, the little d notation, dy dx, as something that we can separate into pieces. So we are going to separate the variables. Now we've seen that in our substitution method, and one would have to go and formally show that these little dy and dx's follow the same rule as fractions, and I'm allowed to do that. But luckily that is the case, and what it does is it helps us solve more complicated differential equations. If I now separate the variables the same as we did for our substitution, I would multiply both sides by dx, and I would have this version of the differential equation, which doesn't show the information as nicely, but I can use this version to get to the answer as well, and that's going to help us moving forward. How I'm going to do that is I'm going to see this now as the left-hand side of an equation and this as the right-hand side of an equation. Now think back to, I'm going to leave a space here, to implicit differentiation. What was that again? Implicit differentiation said I have a left-hand side of an equation and a right-hand side of an equation. I can see them as functions, and if the left-hand side is equal to the right-hand side, then their derivatives have to be equal as well. So I take the derivative of both sides and still get an equal. Now, implicit differentiation, we can see that sort of in reverse here. And what's the reverse of differentiation? Well, in a way, antiderivatives is the reverse. So what I'm going to do is I'm going to take the antiderivative on both sides. Now, the convenience of the differentials is I already have the closing part of this integral. This isn't quite complete until I've resolved each of these antiderivatives, but we just write it like this as an informal next step. Now the key thing in this separation of variables method to solve the differential equation is to just look at each of these sides in isolation. So I'm going to use color. When I have the pink side, there is nothing else. Literally nothing else exists but this side. And when I look at the pink box as a separate question, it is saying that I'm looking for an antiderivative of, when there's nothing there, there's a 1 there, of 1 with y as my variable. So what function in y as the variable has 1 as a derivative? The function is y. Y is my variable. The derivative of y is 1. And on the other side, I have a blue box. So when I do the right-hand side, there is nothing other than the blue box. Now that is a more familiar one because the variable is an x that I usually use, but it doesn't matter what the variable name is. An antiderivative of 2x is x squared. And just like before, we're going to group the constants coming out of each of these at the end. And it doesn't matter which side, I'm just going to put them on the right side, and there we go. And it's the same answer. Now in this case, of course, we had such a simple differential equation, this wasn't necessary to separate the variables and everything. But once I get to the differential equations with y in it, floating around, then it kind of becomes necessary. So by separating the variables and integrating both sides, then just isolating what each side represents, I'm able to find the answer to more complicated differential equations. Let's take one as an example. So let's take, for example, we can actually go to the problems here. Let's take, I don't want to do something too complicated just yet. I'm looking for a nice and easy one. Let's do, let's do this one. Let's do that one. dy dx equals negative x over y. dy dx equals negative x over y. I'm just going to put the negative with the x for convenience, doesn't really matter. This is a separable equation because if I take the y to the other side, it looks exactly right like this bottom box version. So it is a separable equation. Now, to be fair, for our level, when we have y's floating around, it's always going to be a separable equation. I just need to separate it. And after I've put all the y's with the dy dx and all the x's on the other side, then I will multiply both sides by dx. To avoid mistakes, please leave the dx moving until the very last. So now I have all y-related things on the left, all x-related things on the right. I then integrate both sides. Now I have to look at them in isolation, which means the left side has a variable. Let's use color again to highlight what I am looking at. There is nothing for the next few seconds outside of this pink box. Nothing exists. This just happens to be an antiderivative question with y as the variable. And it's asking, what is the function in y that has derivative answer y? Well, it's going to be y squared with a 1/2 correction. When I'm done with that one, I put the constants on hold until the end. I then look at the other side and isolate that as a separate question, just the blue box. The antiderivative of negative x will be negative 1/2 x squared. And then I put it together with just the constants grouped into the constant c. So here, just like before, here I have my general solution. Now, what's often the case in very, very basic differential equations with just x's, my general solution is going to be written in function form with y equal to something in x. Here I still have the general solution to the differential equation, but I'm not going to bother. You can simplify it, maybe multiply throughout by 2 or whatever. I'm not going to solve for y because this isn't a function anymore. This is a more general equation relating x and y values on a graph. Think of a circle and things like that. And how I can verify that this is correct is just by implicit differentiation and simplifying back to the original. So this is just a general solution like before. Just don't care too much to have to solve for y every time, because starting from a more general differential equation, I might end up with something a little bit more general than a function. I still have an equation that relates x and y. So we've moved on to something a little bit more general, and the general solution could look a little fancier as well. So don't worry about having to solve for y each time. It's nice if I can, but it's not necessary. So all we're practicing is separating the variables. Let's see. Let's go this one. Don't want to jump up in complexity too fast. Let's go with that top one. Now I have dy dt, t squared plus 1 over 3y squared. So dy dt, t squared plus 1 over 3y squared. Is that a separable equation? Yes, it is. I think it's a very good habit to do it in 2 steps at least. Keep the derivative in one piece and just make sure you separate the other variables correctly. Then separate the differentials by multiplying dt to the other side, and that will help me have the dt with the whole right-hand side, which it needs to be. Then I integrate both sides. In isolation, the left-hand side is y cubed. In isolation, the right-hand side is a third t cubed plus t, and I group all the constants coming from each one together in a single representation, c. So there's my general solution again. This one I can solve. I don't want to. This is a very nice, clean version of the solution. It doesn't have to be y equal to something. So all we're practicing is separating the variables and what the separation of variables method allows me to do. It's allowing me to solve these more complicated differential equations. Now we'll come to particular solutions in a second, because it's not really any significant step forward. Let's see maybe this first one. Maybe let's go with the very first one. dy dt equals negative y. I don't have any space. All right, so here's our next one. dy dt equals negative y. How would I separate the variables? If I just leave, like my step for creating good habits is to leave the derivative in one piece first and try and get to this box form, where all the other y variables are grouped with the derivative and all the independent variable x or t or whatever it is will be grouped on the other side. So this box is what I'm trying to go for first. Then I'll simply move that bottom differential to the other side. But I've seen people try and do too much at once and then create a separate equation that isn't quite the same. So how I need to get the y to the left. Now you can put, so what I really have here is having to divide both sides by negative y to get negative 1 over y dy dt equals 1. Now I see it, like the box, as a separable equation. I just have to move the dt to the other side to finish it. So negative 1 over y dy equals dt. Then I integrate both sides. Now the right-hand side is going to be super easy, right? It's just going to be antiderivative of 1 with respect to t. It's just t. And I'll put the constants there now before I forget. The left-hand side, I keep the negative out of it. 1 over y with y as the variable. I have to forget what y actually means. I just see the left-hand side in isolation. It's the natural log of y. Now, for our level, we don't care about the most general version of this. If you move on to more formal calculus and things like that, we have absolute values here. I don't care about any of that for this level. Now I can leave it like this. There's a perfectly fine general solution. Perfectly fine general solution. Nothing to it. It's just separating the variables. To avoid mistakes, I prefer keeping the derivative solid and at the very end separating those differentials. Integrating both sides, I just need to practice to see these sides in isolation. That is the main challenge. But it's all just a matter of practice. Practice. Okay, let's see what else do we have here. Let's go with... it doesn't really matter. Let's go with that top one. That's a nice one. It looks a little bit more interesting. Though we'll soon see that in the end, the separation of variables method is very similar every time. E to the negative t dy dt and what's next? Y to the negative 2. All right. Now, technically in general, you have to identify, well, is this a separable equation? Can I use that method? But for us, that's the only method we need to know. The questions will always be suited for that method to work. I just have to do it. So you can, if you want to, get rid of the negative exponents to better see what to do. And then I see, oh, I have to multiply by y squared and by e to the t. And then I would have them nice and separated. Last thing to do, separate the differentials as well to get to my, oops, that's an ugly t. To get to my separated version of the differential equation. Same thing always, we're just practicing, and that repetition helps me to get some confidence. When they're separated, integrate both sides. Now do them in isolation. Left-hand side is just an antiderivative question in y. Antiderivative of y squared will be y cubed with a 1/3 correction. Antiderivative of e to the t with t as my variable is e to the t. Group all the constants. General solution. Nothing to it. Well, not nothing, but this separation of variables method is designed to be straightforward to use and fairly simple if I just know how to approach it. So let's go over to our particular solution group of questions. But we'll see once we have the general solution, the rest is really a formality to find the constant involved. Let's do the first 2 dy dt, 2t over y. dy dt, 2t over y, and my initial condition, y of 1 equals negative 2. All right. Now I'm not too bothered by that extra information because I don't need it until after the general solution. So I need to separate here. Y goes to the left 2t on the right, then multiply both sides by dt, and integrate. The left-hand side, 1/2 y squared. The right-hand side, t squared. And my constants are all grouped together. That's my general solution. General solution. Then I use the extra information that says when t is 1, y is -2. So I plug that in, -2 for y, 1 for t, and solve for c in the constant, in the equation. Well, this is going to be 4, so it's 2 minus 1, which is 1. And then I can go and say 1/2 y squared equals t squared plus 1 is my particular solution. And I'm done. So the main part is still going to be finding the general solution. Regardless of how that was done, using the extra information to find the constant is independent of the method to solve the differential equation. It's in many ways a formality after the fact. If I just remember, I do not have to solve for y. Leave it in whatever nice equation version you want. You can perhaps write y squared equals 2t squared plus 2. You could do that if it looks a little nicer, but I am not going to solve for y. In this more general situation, I don't have functions as answers to the differential equations necessarily. Let's see. Oh, I want to do both of the first two, right? So this is the next one. dy dx equals x e to the negative y. dy dx equals x times e to the negative y, and y of 0 equals 1. All right. So I move all the y-related things to the left. So it'll be e to the y dy dx equals x. Then I separate the differentials as well to have e to the y dy equals x dx. Integrate both sides. The left-hand side in isolation. The antiderivative of e to the y, e to the y. Antiderivative of x, 1/2 x squared. And my constants, my integration constant at the end, I just put it on the right side. Now I can solve for y. I don't have to, but you totally can if you want to. There's just no benefit, to be honest, for these made-up questions. When we get to practical questions, where I'm going to use my answer, which is probably going to be a function, to answer further questions, then yes, I want to clean that up. But right now, they're not going to specify how to present the answers, so whatever's convenient. I like this equation. I'm going to leave it like that. So there's my general solution. General solution. Then I'm going to use my information that says when t is 0, y is 1. So e to the 1, not t, x. X is 0. X is 0 over there. And that tells me that C is equal to E. So my solution in equation form is e to the y equals 1/2 x squared plus E. And there's my particular solution. I am not bothered that I didn't solve for y. There was no need to. There was no practical problem where I have to use this further, justifying that I simplify it. So I don't. The finding of the general solution is always the same, to the point where notice that I actually don't need anything else, even when it is more basic. Let's just make this observation. If I now happen to come across a simple one, actually I don't think there is a simple one without y's anywhere, no. If I happen to have dy dx equals 4x whatever to the 7, I don't need to think of these differential equations as different. They are separable equations. There is just no y's floating around. I would still separate the differentials like this, integrate both sides. The left side is just y, and the right side is whatever the right side wants to be. There is actually, for our level, nothing outside of separating the variables. It works even in the more basic situations. I didn't have to think about this as being a rephrasing of the antiderivative question. No, separating the variables, it's all I need. So let's write that here. Separation of variables. The method works for simple differential equations as well. There is no other method that we need for our level. Let's see what else we can do. Maybe a last question. Now, there isn't much. Maybe this top one. There isn't much in terms of how difficult we can make it. Maybe that top one. dy dt equals 3ty minus 2t. 3ty minus 2t. And I have an initial condition, y of 0 equals 1. All right. So let's have that as our last example and just pay close attention to how I would rewrite this equation to separate the variables correctly. I've seen people, and I don't understand it, but I've seen people just move the y however they want to. Oh, I see a y, I'm just going to put it on the left. Well, I have to still follow the rules of arithmetic. And I have multiple terms here. So it's not going to be that simple. I can't just divide by y, then I create a little y over there. And it's not really separated. So what I first have to do is factor out a t. I have to have multiplication here before I can successfully separate the variables. I also can't move this guy to the left and then say, oh, but all the y's are on the left. Yeah, but what about the t? If I then divide by the t, then there's a 1 over t with this guy, and it just it's not going to work with addition and subtraction. So my separation procedure is really done by way of multiplication and division. So I have to make sure I don't have multiple terms on one side. Once I have that, whether I want it or not, separating the variables is going to take the 3y minus 2 to the left. And I can then finish that by multiplying both sides by dt. Yeah, some people like to put the dy at the top. I'm not one of those people. Integrate both sides. And then I have to think a little bit, but the right side's easy. That's a 1/2 t squared. I'll just do my constant now so I don't forget. What's happening on the left here? What's happening on the left? Now, you could go and say, you know, I'm just not comfortable with this. Let's just recognize that this requires a substitution and do it on the side. Use my u to say it's 3y minus 2. Then the derivative, the y is just my variable, like an x or a t for the moment, is 3. So I separate those variables. Sorry, that's a little ugly. As 3 dy. So that means I need to see a 3 there, and I pay the price. Then I have the 1 over u. 3 dy is the same as du, and I know that is 1/3 natural log of u. I ignore the constants right now. I go back and say 1/3 log of 3y minus 2. I can go and be sure, be safe. Or I can totally guess and check my way through it. It is totally up to you. You have these methods that you can't forget. Substitution is still there. I have the potential of one of these sides, or both perhaps, being a reverse chain rule situation. It is possible. Regardless, there I go. Okay. Now, yeah, I could solve this. It's arbitrary. I don't have a need to do that. Here is my general solution. I don't feel that there's anything to gain if I don't have a follow-up question. I use my extra information, and it says when t is 0, y is 1. So I plug that in. Wherever I see a y, it'll be a 1. And wherever I see a t, it'll be a 0. Let's move up a little bit. Not a lot of space left. Let me just simplify this guy. This in the bracket is a 1. Log of 1 is, it's the power of e that would give me an answer of 1, which is 0. So that means that c is 0. So that means my general solution can be updated to a particular solution like so, with c equal to 0, and that is my particular solution. This is still faster than if I try to solve for y, run the risk of a mistake, then I still have to plug the initial condition in to get the value of c. It'll just reduce to the same thing. There's no benefit. Once we have a practical layer on top where we need a function to answer follow-up questions, then there certainly is a point to simplifying the solutions by solving for y. So have a look at that. Are there any questions so far? We are now ready to move into our, well, not today, but next time, move into our final chapter where we will see a fair number of applications of these differential equations applied to growth and decay problems. Let me just, I think I have our schedule open here somewhere. Yes. We are over here on the 6th. Now, we are going to be able to squeeze in 2 growth and decay problems before the midterm next Monday. And then after the midterm, we will do a few more, which may be included in the final exam. I believe our final exam is on the 24th, but double check on your end as well. I'm just going on memory now. Yes, are there any questions? We are very close to the end. 24th, yes. Don't ask me the time. I need to go look it up again. Could be the morning, 9 a.m. Yes, but then at least you have the rest of the weekend, right? So morning might be better. All right. Until tomorrow then. See you then.